Hello. Today I'm going to do a demonstration of some of the equipment we have in our beam pumping lab at the University of Texas. We have used this in past years for experimental work, and it's a great demo. So we're going to do the demo today. I'm going to start back here at the back of our pumping unit, and I'm going to start with the prime mover. The prime mover in this case is this little gray motor. The gray motor obviously is an electrical device, and it has this little sheave on it that connects by this fan belt to the orange sheave, much bigger sheave, that is actually on the input shaft to the gearbox. Now, you may recall from our lectures that a small sheave driving a big sheave is the same thing that's going on in our gearbox, where we have small gears, like this small sheave, driving bigger gears, like this orange sheave, and anytime that happens, it's speed reduction. So all of this, what you see, the sheave on the motor and the orange sheave on the pumping unit, and what you can't see, the gears inside the gearbox, are attempting to slow the speed of this motor down. This motor actually is going to rotate probably something like 1,100 revolutions per minute, and we've got to somehow reduce that speed to the speed that we want our pumping unit to go up and down. So these external sheaves are the first step in that, and then the gears in the gearbox are the second step in that. All right, now once the gears start turning, this big output shaft is the last shaft in the gearbox, and it's connected to this little green crank. There's a crank on each side. The crank has a bearing on the end of it. This is actually a bearing. It's called a wrist pin or a Pitman Arm Bearing. And what it does is when the crank goes around in a circle, it allows this Pitman arm to basically move up and then back down. And we'll see that in motion here in a minute or two. So the Pitman arms are going to be the device that takes the rotary motion of the cranks and converts it into an up and down motion of the beam of the pumping unit, and finally, the rods out at the front of the well. Now these Pitman arms come up to this cross member that's called an equalizer, and the equalizer is attached to the rear of the beam. It also has a bearing because it has to move back and forth with the motion of the beam. Now the beam obviously is this big piece of H iron here on top. It has space on the back with some holes in it where weights could be applied. Now there are no weights on this pumping unit because we don't need them. But if you needed some extra weight to counterbalance, to offset the load being picked up from the well, you would put them back here. So this is a beam balanced pumping unit. Now if we'll go forward, there's a supporting post here that is holding the beam up high enough so that we have enough room for the stroke at the front to take place. This is called the Samson post, meaning it's going to support all of the load, including the beam. That happens here. And there's a bearing that allows the beam to move up and down on top of the Samson post. That oftentimes is called the center bearing. Now I'm going to walk around here in front. So at the front of the beam, we've got this curved orange piece that people call the horse head. I mean, it kind of looks a little bit like a horse head. And it's curved because when the beam moves up and down, it's moving actually in an arc. And you don't want the rods to get caught in that arc and bent. So the horse head allows for the curved arc of the beam to not get in the way of the up and down motion of the rods that are going down into the well. Now at the front of this horse head, there's this wire bridle. We have a little bitty bridle here, not carrying much load. The bridles can get really big depending on how much load they're supporting. The bridle hooks the carrier bar to the top of the horse head. That's where the load is supported, up here at the top of the horse head. The carrier bar is locked in place by this clamp around the polish rod. Here's the polish rod. Now, before we talk about the polish rod, there's this thing here in the middle. This is actually a load cell. It's called a dynamometer, and what it does is it measures the load that is being carried by the polish rod at this point throughout one cycle up and down of the polish rod. Now, this is a modern one, and what makes it modern is inside this is not just the load cell. There are also some accelerometers that detect the change in acceleration of the polish rod. And if we can determine the change in acceleration, that can be converted to velocity, and velocity can be converted to position. So the accelerometers that are embedded in here can allow us to determine where in the stroke are we for any measurement of load. And to make it completely modern, these guys have a telemetry device, not this wire, a telemetry device that can communicate wirelessly to our computer that looks at all of this information. So the dynamometer is installed on this particular pumping unit, and it is the definitive diagnostic tool for beam pumping troubles. All right, so the polish rod now is this shiny rod, and it really is shiny. It's shiny because it's got to slide up and down through this thing. This yellow cap is called a stuffing box. And in the stuffing box, there are some rubber rings. If I tighten down on the stuffing box, the rubber rings are squeezed tighter and tighter against the polish rod, and that prevents any liquid from getting out at the top of the well. If it weren't for the stuffing box and the polish rod, well, we'd have a heck of a mess on our hands. All of the liquid just be gushing out here at the top of the well. So the stuffing box and the polish rod prevent that. Now the rods that go on down to the pump, they're screwed onto the bottom of this polish rod. We're not going to see them right now. We'll look at them later. All right, so to finish our surface description here, this is the wellhead that's attached to the top of the production casing. And sticking up out of it is a green piece of oil well tubing. So the rods are going down through the tubing to the pump. And when the pump is cycled, the liquids are pumped up inside the tubing. They can't get out past the properly adjusted stuffing box, so where do they go? They exit at this red flow tee, and they go sideways. You can't see it, but there's a white tank behind me. There's a PVC line that goes from this exit to the white tank. And then the white tank has a pipe that goes back downstairs to where the pump is, and we just cycle this over and over again. A couple of things I should comment about our setup here. This is not what you would exactly expect to see in the field. What's missing is there's no fence around all of this that would be there to prevent people who had no business being close to this machinery, hopefully keep them away, keep them out. And back here on the back where our orange shiv is attached by the fan belt to the motor, there should be a belt guard there. It's off now so that you can see what's going on. It's a good teaching tool, but it's not safe. In the real world, a belt guard would be there to make this safe. All right, so before we leave here, I'm going to go back and I'm going to turn our pumping unit on, and we're going to watch it go through a couple of cycles. And then we will go downstairs and take a look at the pump. So of particular interest is the motion of the Pitman arms back here. You'll notice the cranks are just going around in a circle, but because of the bearings on the Pitman arms and on the Equalizer, look at what they do. Right now, with the cranks at the top, the Pitman arms are pushing up, and as the crank goes around, they're pulled down. So this is how the rotary motion of the cranks turns out to be an up and down motion, a linear motion, reticulating motion of the. And of course here on the front, polish rod's just being raised and then lowered down into the well. So the pumping unit on the upstroke is picking up the weight of the rods, the weight of the fluid, and overcoming any frictional forces that might be in the well. On the downstroke, interestingly enough, coming down, the pumping unit doesn't push on this. All of the weight of the rods must fall back into the well pulled by gravity. So there's no force pushing these things back down into the well other than the force of gravity. All right, now we're ready to go downstairs and take a look at the pump. All right, we've moved downstairs. The pumping unit we left 3 floors above us. So our well is only 3 stories deep, but it has rods that attach the polish rod down here to the pump. This is actually the plunger of the pump right here. And you can see there's the coupling that attaches it to the rods that go back to the pumping unit. So the plunger, in this case, has this shiny silver piece. That is actually the plunger. That's the seal. That's what keeps liquid from above for finding a ready pathway back around the outside of the pump and going back down to have to be pumped a second time. Now this seal doesn't look like much of a seal. What causes it to be a seal is the gap between the outside of the highly machined plunger and the inside of our transparent tubing. That's very, very close. So there isn't much space for fluid to flow backwards. There isn't much pressure above it to cause that to flow backwards. But this, in a real pump, would be called a metal-to-metal fit. The metal-to-metal fit means we've got a little gap in here. The gap is part of the pump design. Normally that gap is between 0.002 and 0.006 inches. So it's pretty small. Now, the plunger is hollow. It's got to be, or fluid couldn't get from below up above. Now, we got a valve on the plunger that moves up and down with the motion of the pumping unit. It's called the traveling valve because it travels. And it's this ball and seat right here. Now, right now, nothing's happening. The pump isn't on. Nothing's moving. You'll notice that gravity has pulled the ball down and it's sitting comfortably on its seat. So this would be a closed position for this valve. There's another valve in here though. The inlet into the barrel of the pump is down here. It's another ball and seat. This is called the standing valve because it doesn't move, it just stands there. But it's going to open to allow fluid from the reservoir to flow up into the barrel and stay there. Now, the fluid that we're pumping is a mineral oil. It's this light color, this very light shade of yellow. That's mineral oil. That's coming down from our tank. The pumping unit is going to pump it back to the surface through the action of this pump. Okay, now we have changed this well bore a little bit. It used to be this was just purely a vertical well, and it's vertical down to about here. And then you'll notice we've got this fitting that transitions quickly to a horizontal part. So this is our poor mock-up of a horizontal well, and it's going to show lots of the same problems that a horizontal well might have. So how do you get reservoir oil from out here in the horizontal part up to the pump intake, which is actually right there? Well, we got to have some way for the reservoir to flow oil through the standing valve to keep the barrel full of liquid. All right, that happens in this mock-up by this tube you see placed on the bottom of our pump. This tube goes all the way down, and it's lying on the bottom part of our horizontal extension. Gravity pulls it there. All right, now we're looking out here at the end of our horizontal piece of pipe. You'll see here is the extension that we had bolted onto the bottom of the pump. It's coming all the way down here to the end, and we put a weight on it to make sure it stays sitting on the bottom. If this were a real tube, it no doubt would be made out of steel and would just sit there by itself, pulled by gravity. Since this is a plastic tube, we've weighted it to make sure that it lays down against the bottom. So how can oil get into the pump? Well, it's got to go in right there, right where our shiny gray piece of steel is. That's the end of this tube. And I like to call this tube a dip tube. Now, this dip tube clearly is in our horizontal part of the well. That's because our horizontal part's not very long, and we don't have much room to go from vertical to horizontal, so this is the best we could do. I don't think anybody in the real world would put a dip tube like this all the way out in the truly horizontal part of the well because of the fear of producing frac sand. If you get any frac sand produced in here, it might plug up the inside of this dip tube, which would be bad. Or it might get around the outside, in which case the dip tube is stuck, which is probably worse. So this idea, and I think it's a good one, shouldn't go out into the long horizontal section. Where it should end is somewhere in the curve, somewhere between the transition from vertical to truly horizontal, all right? And the beauty of that, we will see in a moment, is that it allows the bigger piece of wellbore casing to act as a natural gas-liquid separator. The gas wants to move along the upper section of the well, even if it's in the curved part of the well. And the liquid, when it gets to the intake here of our dip tube, will have the tendency to fill up the dip tube. It's on the low side of the hole. That's where the liquid is preferentially going to collect. So the dip tube has some advantages here. All right, so I'm going to go back and I'm going to turn our well on, and we're going to start out looking at our well where everything is fine. All right, so we're going to go back and we're going to look at the action of our pump. Let's just review real quick. We've got a standing valve which opens during the upstroke, because when the plunger is moving up, it creates a low pressure area inside the barrel. So it doesn't take much well pressure to pop that valve open and start flowing up the dip tube and filling up this barrel. Now the barrel, such as we can see it right here, is full. It's got our yellow mineral oil in it. Now, that is the purpose of the standing valve. It opens during the upstroke and allows oil to enter and fill up the barrel. During the downstroke, though, whatever fluid is trapped in this barrel, it's now compressed by the downward motion of the plunger. And if we have liquid in here, it doesn't take much downward motion to build up plenty of pressure to hold the standing valve closed. Now, while all that's going on, the traveling valve during the downstroke has got to open. We're compressing the fluid under the plunger, so when we have enough pressure under the plunger to overcome the pressure above the traveling valve, it opens. Now the plunger, which is hollow, just falls through the liquid-filled barrel until it gets to the bottom, and then it reverses course. The pumping unit now is picking the plunger up, and when that happens, the fluid pressure above the traveling valve becomes enough to force the traveling valve to close, and it stays closed. And then we lift one stroke length at a time, liquid towards the surface. All right, so I'm going to turn this on, and we're going to see what a pump that is working 100% appropriately looks like. So I just turned the pumping unit on at the surface. And what do we see? Well, let's start out at the beginning of the upstroke, right now. Notice the standing valve opens. You can see it open just a little bit. That's allowing new oil to enter from our reservoir up our long dip tube. It's filling up the barrel. Now there may be a small amount of air entrained in there. That's of no consequence to us. What happens on the downstroke? Well, it closes. The motion of the plunger is compressing the oil and holding the valve shut. So it is open now. On the downstroke, it's going to close and stay closed. The traveling valve, on the other hand, is open during the downstroke. It's compressed enough pressure to pop it open, and then it's closed on the upstroke, held that way by the hydrostatic pressure of the fluid to the surface. Now, I want you to just look at the motion of these valves. They're not violent. They're a little lazy. They kind of open and then sit down and close. Nothing adverse is happening here. I've got a barrel full of liquid on every stroke. This is what this pump was designed to do. Now I'm just going to let it pump, and in a little bit, we're going to run out of liquid. And we will go and look at what that does to our pump. And then we'll probably go back down to the end of the dip tube and have a look at that. But for the moment, whatever air is in our well is free to migrate up the outside of our pump to the surface in the annulus. It's acting as a wonderful gas-liquid separator. Okay, now the dip tube just became uncovered. The oil down at the end of the dip tube is no longer enough to keep it submerged. So what comes in down there? Well, whatever oil can get in, plus some of the gas. And I know that's happening now because what do I see coming into the barrel? It's not just oil. See the bubbles? They came from somewhere. They came in down at the end of the dip tube. Now this is not good news for our pump. Number one, if the barrel isn't filling 100% on every stroke, I am paying money to make that pump go up and down, and I'm getting only a fraction of the barrel full of liquid on every stroke to the surface. So that's not good design, but it gets worse. So let's take a look now at the action of these valves. So let's start out with the standing valve. We're going to look at it at the beginning of the upstroke. You see all the air coming through there? Do you see the frantic motion of the steel ball? You might even be able to hear it. The steel ball is chattering. It's actually colliding with the steel cage that's holding it in that position. So this collision is terrible wear and tear on the valve, on the seat, and on the steel cage that's holding it all in place. And this chatter is caused because when the air enters through that valve, it expands. You can see the motion of the gas expanding. Watch the froth and foam that it makes right there. So this expansion is what's causing this detrimental valve chatter. All right, well, what about traveling valve? Well, it's got the same problem. So let's take a look at it now. It opens about right there, and you will notice it's got all of that gas that's now expanding across the traveling valve. It's causing it to chatter. Now, it doesn't make the noise like the standing valve did because it's got a plexiglass cage, but collision is happening here too. So the wear and tear on these valves in the pump just went up. Now, we said that there's compression going on. Let's take a look at that. Now, on the downstroke, that traveling valve is closed. It doesn't open until it gets to about right there. What has happened between the start up here and where it opens right there? Well, it's compressing the air that's trapped in the barrel between the top of the liquid. All of this is just air. So I'm compressing the air to the point where I've got enough pressure to push the traveling valve open, and then I go through the air expansion and the valve chatter. Now, this is called fluid pound, which is a bit of a misnomer. Let's take a look at this again. Let's watch where the level of liquid is. It's about right here. The traveling valve opens up here. So you don't actually run the plunger into the relatively incompressible surface of the liquid. That really doesn't happen. But we are compressing the gas to the point where the traveling valve opens, and then our chattering gas expansion starts again. So this is something we would prefer not to have happen, all right? How can we prevent it? Well, we talked about that. One of the goals of beam lift is to keep up with the changes in the reservoir. So if we're down now, like this looks like, where we've got maybe, what, a third of the barrel full of liquid, if we can't do anything to get more liquid flowing into the wellbore, our only solution is to slow the pumping speed down. We might slow the pumping speed down 2/3 because we've only got a third of the barrel filling with liquid. If we did that, then we would have enough time for the barrel to fill, and we would have just liquid in here. All right, so I'm going to put a little more liquid in so we can kind of get back to where we started. I want to end this by reminding ourselves of what the perfect ideal conditions for this pump are. So this shows the end of the dip tube at the extreme conditions we just looked at in the pump. You'll notice the dip tube now is really kind of up out of the liquid. So whatever liquid can get in there has a hard time, but there's no problem with the air getting into the end of the dip tube or, in a real well, natural gas. So the dip tube needs to be kept submerged if at all possible, and then you avoid the problems we just looked at the pump. So this is the dip tube again, submerged. You'll notice that the oil level is enough to just keep it under the oil. So the oil preferentially is going to go into the dip tube and up to the pump intake. the air or the natural gas is going along the top and exiting the annulus and headed into the surface. So this is again allowing our curve and our wellbore to act as a dandy downhole gas liquid separator. All right, so we've submerged the dip tube again. Now we have oil coming into the dip tube, and we're working out the last of the trapped gas in the dip tube. But again, this is what we believe a perfect happy pump should look like. The valves are opening and closing as they should, but they're not violent. They're not chattering. There isn't the collision between valve and seat or valve and cage. So this is one of the goals of trying to keep the pumping equipment balanced with what the reservoir production can be. It pays dividends in pump life.